Okay, hello everybody again. And then this is lecture 2, part 1 of signals and systems. And now we're going to start talking about signal energy and power. Not because you're going to be calculating a lot of energy values and then power values in the course, but it's good to know because signals and systems is the foundation of communication theory, wireless communications, communication systems, random signals and systems. So it's very important to know these definitions. And although you might not be using that extensively in this course, it will bite you back if you don't get a good understanding of them. So we're going to start off with that, okay? This is a one-pager lecture. I don't think it should be too long, but you never know. Sometimes your boy likes to talk. Lecture 2.1, signal energy and power. So if you have a circuit over here, simple circuit, one resistor, one voltage source, and one current source. I should probably write that this is V of t. Okay, so this is my voltage source, this is my current in orange, and then this is my resistor value, is V of t. If I ask you what's the power in this resistor, you're gonna tell me it's Vi. Okay, we learned that in circuit theory 1. If you don't know that, God help you. The current is voltage over resistance, which is V over R. Again, we learned that in circuit theory 1, Ohm's law. So I plug it in here. And then the final equation is V squared over R. Again, you probably have seen this before, and I should not have explained it, and you would still be okay. Okay, but we also know by a physics definition that power is energy over time. Okay, so you have power is equal to energy over time. Now, yes and no, because again, we're trying to find a general definition. So we can't just say energy over time. We have to take a small piece of the energy, dE, a differential of energy over a differential of time. So this is power, d equals dE over dt. Now let's say we're trying to find the energy. This looks like a one-dimensional differential, like one variable differential equation. Okay, so you probably learned how to solve this in calculus 2. So you're going to take the dt, and then it's called separation of variables. So you're going to take the dt, you're going to bring it to the other side. So your differential of energy is equal to power times dt. You have this equation. Now, if you want to find the total energy, you're going to have to integrate both sides. So the total energy is the integral of dE. We're just going to integrate from one time t1 to some time t2. So this we're going to integrate from t1 to t2 as well. And then this is your equation. So the total energy is given by this equation. Okay. Now remember, the power that we have over here, which is derived over there to be V squared over R. So we're going to take V squared over R, which is the same as 1 over R times V squared T. We're going to plug it in here. And if you're smart, you will notice that this 1 over R can come outside, okay? Now, I want you to notice something. This is a circuit kind of explanation to make you get some intuition about what the energy is. But now when you're talking about a signal, you're only talking about the voltage and the current, okay? If you think about it, yes, if you're looking at units, volts over ohms gives you units of energy, okay? Or sorry, volts squared over ohms give you units of energy, but it's not, what am I saying? Voltage is in volts. Volts squared over ohms give you units of power, not energy. It's kind of bakwas. I'm yapping. Whew, that's how you know I'm in summer. I'm not in like school mode or anything right now. Anyways, let me rephrase that again. A volt squared over ohms give you units of power. Okay, but when you're talking about a signal, that 1 over R, I want you to forget it as a 1 over R resistance. Just think about it as a integer scaling factor. You're scaling your voltage signal by some 1 over R, all right? The 1 over the voltage itself, the voltage square, that's still your signal. Okay, you just integrated it over T1 and T2 to T2 to find what the energy is. Okay, so the 1 over R you can multiply it any time. Okay, and now if you want to have a general definition for a signal, usually we ignore that 1 over R. All right, for a signal we ignore it totally because kind of think about the resistance as being 1. 1 over 1 is 1, so it doesn't really change anything, right? That's a good way to think about it. So the average power is given by this definition. You need to add this 1 over T2 minus T1. I'm not going to go as to why that's there. You can do the research on your own if you want. Do you know where that equation comes from? It's just the average power equation, or average value of a function, or something like this that we'll learn in calculus 2. We're just applying the definitions here. So average power is 1 over T2 minus T1, integral of T1 to T2 of PT dt, but PT is your power, which is this thing, and I'm just going to replace it here. So that's your average power definition, okay? Now, for any continuous time signal x of t, the total energy in interval t1 to t2 is the integral from t1 to t2 of x of t squared dt in absolute values. Okay? So now you can have a negative function, right? If you have a function that's negative x squared, for example, right? You can have a negative energy that's negative. Does not make sense. So the best way you can make something that's negative a positive is you put it in absolute value, and now you have minus x squared, which is giving you x squared. Does that make sense? Now you might be wondering, well, yo, why is there squared here? Well, just by analogy, sorry, a voltage squared over ohms is power, right? So you have to square to get power, even though you're not dividing by resistance. So that's why you have a square here. Physical intuition. Time average power. Again, we're going to use the same definition we have over here, except we're going to replace the 1 over r v squared t by the definition that we used over here. That's all it is. That's your time average power. Okay? Now, for discrete time signals, the total energy, again, it's the same principle here as to why we have absolute value and why we have squared. But for discrete time signals, you can't integrate because your time scale is discrete. And if you just integrate, if you have looking at a signal from n1 to n2, some values n1 to n2, you're gonna have to do the summation. Okay, the summation of your signal from n1 to n2, your signal in absolute value squared from n1 to n2, and that gives you the energy. And now the average power here is this equation. Okay, so you got x of n squared from n1 to n2, which is same to but same as that one. The only difference is getting divided by 1 over n2 minus n1 plus 1. Okay, now if you notice over here, for the integral, we just have t2 minus t1. But for the sum, we have n2 minus n1 plus 1. Now, if you're a real one, here's what I want you to do. I want you to go do some research about why we have a plus 1 here in the discrete time domain and not the continuous time domain, and then comment down in the video. Okay? If you do that, yeah, my respect. And then we're helping each other out here, and I want to make this channel a little bit interactive. So if you do that, that's going to be pretty good. Find out why there's a plus 1 here. Okay? Now, if we have infinite time interval, let's say you have an interval that goes from negative infinity to infinity for the continuous time domain, and then negative infinity to infinity for the discrete time domain. So your energy, okay, instead of calling it E total, we're going to call it E infinite, okay, for both continuous and discrete. Now, before, you were integrated from some T1 to T2, okay? Now, let's say you were integrating from the period to the period, from minus period to the period, right? It could be any value. For some reason, we just picked minus t to t, okay? And now the only thing we're going to do is we're going to integrate from negative infinity to infinity instead to get that infinite energy value, okay? The infinite energy value, it could converge. You could have an actual physical value for it, but I don't know why we call it the infinite energy value, okay? So you're just integrating from negative infinity to infinity of your signal absolute value squared. And then for discrete time domain, you're just going to do the summation instead, and you're not going to do integrals because it's discrete. Okay. Same thing for power too, but power is a little bit tricky because here there's no factor in front of that integral. In power equations, you have a factor in front, so you got to take the limit as to that factor in front goes to zero. Sorry, goes to infinity. Okay. So we have 1 over 2t. Why we have 1 over 2t here is because here we have 1 over t2 minus t1. In our case, t2 is equal to t. t1 is equal to minus t. If we do t2 minus t1, we have t minus t, which is equal to t plus t, which is equal to 2t. Okay. So that's why we have 2t here. So this is your equation. And then you do that integral. You scale it by 2t, 1 over 2t, and you take the limit when the period goes to infinity. Okay. Same thing over here. Okay. Same thing over here for discrete time signal. Is you're going to do the sum. You're going to scale it by 1 over 2n plus 1, and then you're going to find a limit when n goes to infinity. Okay. Now we got 3 different classes of signals. I'm just going to read over them here because I mean, there's not really much to talk about them. You know, it's just good to know. So you're going to have to, if you memorize that, that's pretty cool. Okay. Class 1 is finite total energy. So that's when your E infinity is less than 0. So that's 0 average power. Okay. If you do p infinity and you take the limit as t goes to infinity of infinity over 2t, you will get 0. And that's how you know that this is an energy signal. Okay. So you can maybe ponder upon that class a little bit on your own time. The class 2 is finite average power, p infinity. For p infinity greater than 0, you got infinity equals infinity. So this is a power signal. Okay, it's called a power signal. Now, when you have neither p infinity or e infinity being finite, then That's in the class 3. Okay. I don't remember having these show up when I took the class, but I guess it's important to know. Although I will admit that I have never really used the term energy signal or power signal in future classes, so I'm just going to mention them there just in case. So, energy signal, total energy E infinity is infinite. I can't speak. Total energy E infinity is finite. So E infinity is between 0 and infinity for P infinity equals 0. This sounds like a bunch of gibberish. Power signal, average power of P infinity is finite, P infinity is less than infinity, and then E infinity is equal to infinity. So memorize these things, keep it in your head. It could help you out. Okay, so that's lecture 2, part 1 of Signals and Systems. Hope you had fun. If you made it to this part of the video and if you like my teaching style and you think I'm providing a lot of value and you think you're benefiting a lot from the videos, especially you watch my previous videos, maybe Electronics 1, maybe you're gonna watch the Electronics 2 series, you watch the Cookies and Cram, and you want to be tutored by me, I will have my Instagram linked in the description. You can send me a direct message there and then we can talk about how we can make that happen.